Hi, everybody. Welcome back. This is another lecture from OpenStack's Intermediate Algebra here from Austin Hoggett. Today's section is going to be continuing with our conversation around rational expressions, talking about how we add and subtract in instances where we either have common denominators or not. We'll also talk about how to find the least common denominator of a rational expression. So rational expressions, we mentioned before, can be treated a lot like fractions, and it's still true in this case. Instances where we want to add or subtract rational expressions that already have a denominator is the same. Functions, much like how we would do so with a fraction. We just add the numerators together. So you can see here again a definitional sort of relationship between how we would add two rational expressions. Again, P and Q here and R are all representative of some type of polynomial. So it's not as though I'm adding, 1/3 plus 2/3 to get 1 plus 2/3. We're actually saying something more akin to, if I have x squared minus 9 over x plus 4 over x, the solution is x squared minus 9 plus 4 all over x. One thing to keep in mind is the idea that these are now polynomials. When we talked about polynomial addition and subtraction, the key was understanding that we treat these polynomials as their own entity. This is a critical thing to understand when it comes to addition and subtraction of our numerators. Because these polynomials could be subtracted, for instance, we might find that some changes to the signs becomes necessary to contend with as we're doing these operations. And I'll point out an example of when that's the case. As well as the operation itself, we will also need to be able to simplify our result. So let's look at this first example together here. I'm asked to do the addition of two expressions, rational expressions, that have the same denominator. So based on our conversation a second ago, we should say, well, the numerator here should be added to the numerator here, and we'll keep the same denominator. So 11x plus 28 gets added to x squared. So as it's written, my parentheses are sort of unnecessary. But again, I want to emphasize the idea that the numerators here are their own sort of entity. I should kind of condense them with the parentheses, or at least associate them together with the parentheses. Rearranging this a bit, because they can't actually be added together as like terms any, means that I would end up with an expression like x squared plus 11x plus 28 all over x plus 4. And we might think that we're done. That, is technically the solution. However, we have a result that could potentially need to be simplified. And so I would need to think about how to factor and reduce any common terms that show up. In our example here, the numerator x squared plus 11x plus 28 is a trinomial that could be factored using the AC method. Factors of 28 that add up to 11 would be 7 and 4. So we could actually factor this to get x plus 7 times x plus 4, which would make for a common factor between the numerator and denominator. Since that's the case, we can reduce this finally by dividing out and leaving us with a final solution here of just x plus 7. So again, the parentheses here really only serve the purpose of manipulating how we consider the actual operation of adding our numerators together. I just rearranged the terms in this case, but had it been subtraction, that would mean that some signs needed to be changed for that second term. As well as actually getting a solution or adding the two expressions together, we needed to simplify, which is really common. So we still have to consider that on occasion. Let's look at another example. Before we look at the next instance, we're going to consider an example of finding the LCD for some rational expression, because that's necessary in order to be able to answer questions where the denominator is not initially already the same. So how do I find the LCD? Well, think back to our conversation around finding the LCD for fractions. We started finding the LCD by considering what are the factors of each of my denominators. So for instance, 12, we could factor into 2 times 6, which is itself 2 times 3. 18, we could factor into 2 times 9, which factors to give me 3 times 3. So in this instance, I just write out all the factors of my given expression. If they're numeric values, that would be similar to how we deal with fractions. If they're rational expressions or polynomial expressions, we factor them using all the litany of techniques presented previously. To actually identify the LCD now, we would look at our list and identify anything that we see duplicated in each of those. So there's only a pair of 2's and a pair of 3's given, but I also have some other values here. So we would end up multiplying through all the leftovers as well. Well, the product here gives me 36, which is the LCD value between 12 and 18. So in order to be able to add these two fractions together, we need to have equivalent expressions for each that now have the denominator that we want, 36. So how do I create an equivalent expression that has the denominator that I desire? Well, let's look at, for instance, 7 over 12. We want the denominator to be 36, but to create the equivalent, what we need to do is multiply by a missing factor. By multiplying it by the numerator and denominator, we create an equivalent fraction without changing its value, just the look. So what factor is missing? Partly, we can go back and see that the only factor that we are missing is the extra 3. So 12 factored to give me 2 times 2 times 3. Well, the LCD needs that last 3. And so we can replace our constant, our mystery constant here at least, with that numeric value to create the equivalent. So it turns out 21 over 36 would be the equivalent fraction that we need to continue the problem. So I won't finish this particular example, but that's sort of where we're starting at in a case where I'm asked to add two rational expressions that don't already have some common denominator. We've got to be able to identify that LCD value and then recreate the expressions. So let's practice that facet first before we move on to the operation. Here's an example asking me to identify the equivalent expression for these two terms. I'm given initially what you see at the top, the expression 8 over the trinomial x squared minus 2x minus 3. So my denominator is what I'm really interested in here. What does this factor to give me? And similarly for the second term, I need to know how is this trinomial going to factor? Also that we can identify that LCD value. So given these two trinomials, we can use the AC method when we would discover that. In this case, we would factor the trinomial to get x minus 3 and x plus 1, x plus 3 and x plus 1. So just like before with the numeric values, we would say, okay, if there's anything in common, we'll only put it as part of our LCD the one time. And we just simply list all the other factors involved. So we also have x minus 3 and x plus 3. So that is what my expressions should look like. That's the denominator that I desire for each of these. So the original expression here, 8 over the trinomial, and I'll put it in its factored form, needs to be written with an equivalent statement that has the LCD values that we desire. So to create that equivalent, all we need to do is multiply the numerator and denominator by some missing factor. So what's the factor that's missing? Well, it's x plus 3 in this case. So my equivalent statement here is 8 times x plus 3. And we can perform a similar task for the second expression here. Again, my numerator stays the same, but we'll write the denominator in its factored version, x plus 3, x plus 1. We would like an equivalent expression that has the correct LCD value in the denominator. So what is the missing factor in this case that gets us to that? Well, now the missing factor is not x plus 3. It already has one of those. What we are missing is the x minus 3. So my equivalent here is given as 3x times x minus 3 in the numerator all over our LCD. So this is typically the first task when we're asked to add or subtract rational expressions. We've got to be able to identify through factoring what the LCD should be, and then recreate the equivalent expressions for each of our terms. Often that means going back to identify what's the missing factor and including it as this extra piece that we multiply numerator and denominator by to create the equivalency. So let's apply this in a case where we're asked to do that very operation. In fact, we'll use the exact same numbers that we showed a moment ago. So when we add or subtract rational expressions, if they've already got the same denominator, great. We can just add the numerators, subtract the numerators together. Simplify if necessary. If not, we've got to go through this process of identifying the LCD and then rewriting the expression using the LCD as our new denominator. So we saw a moment ago that our two expressions could be rewritten in the following format. And our example is going to use those exact same expressions. So here's what the question may look like. Add for me together these two values. So again, we identified the LCD as being x plus 1, x minus 3, and x plus 3. We gave an equivalent for each of these where we showed that our numerator for the first term needed to have that missing factor, which would have been x minus 3. And for my second term, what I'm missing was the other factor, x minus 3. This typically is the longest process of any of these problems. Being able to identify the LCD means knowing how to quickly factor and create your equivalency. Now that we can actually add these together, we end up in the numerator with two expressions. Obviously, my denominator stays the same. Before I actually go through and add these together, though, consider doing some distribution on the expression here and here. They are going to be added together, but it's a lot easier to do that if we sort of simplify them first. So for instance, we could get 8x plus 24 in our first bracket. Added to 3x squared minus 9x in the second. This is where it becomes critical to understand that the numerators need to be associated together. If this had been a subtraction problem, for instance, notice it would change the signs of all those terms in the second parentheses. So we've got this just about wrapped up. Because this is actually addition and not subtraction, I can kind of ignore my parentheticals and just try to combine the like terms. In that case, I get something like 3x squared for my first term. 8x minus 9x is going to give me minus 1x, and plus 24 at the end. All of this over my LCD value. So now we've got pretty much everything completed. However, we could still consider the question, does this factor or continue to factor in such a way that it would reduce? So I could pose the question here using, let's say, the AC method. Are there factors of 72 that add up to -1? And in this case, there is. I could say that um, there are factors of 72 that add up to uh, +1, but not -1. So although I could pose the question here, I suppose there's not actually any solution. So that numerator does not appear to reduce any. My initial consideration was that, 3 times 24 gets me to 72. But we need to figure out, are they going to add together to give me -1? And if I consider my list of factors for 72, we could say 1 times 72, those obviously won't work. 2 times 36 isn't going to work. 8 times 9 is maybe the closest I can think of that has a difference of 2, but I can't figure out a way for them to multiply to be positive and then somehow add to be negative. So it appears like the AC method fails us and it's reduced as much as possible. That's not always going to be the case here, but it does in this instance, which is great. This is already pretty complicated stuff, and so by the time we get to a solution, we don't want to goof it up at the end by not considering if we have the simplest answer. Let's try another example though. So here I'm asked to do the subtraction. And again, I want to start by identifying the LCD value for what the denominator should be, since obviously these aren't initially the same. So what are the factors of y squared minus 16? Well, this is a difference of squares, so it should have factors that produce a product of conjugates. So y plus 4 and y minus 4. What are the factors of y minus 4? Well, there aren't any. It's just going to be y minus 4. So what is the LCD? Well, I've got at least one thing in common here, y minus 4, so that's part of it. The other factor given is y plus 4. So it looks like really only one of these terms needs to be rewritten. An equivalent way we could state this is 8y over y plus 4, y minus 4. And for my second term, the denominator already has a y minus 4, so we need to introduce y plus 4 to get the LCD value that we need. So now I can add these together, and of course the denominator should stay the same. Y plus 4, y minus 4. Just like before, and even more critically so now, because this is a subtraction problem, I need to simplify my two numerators before continuing. So we will have this numerator minus this numerator. So we have 8y, which is already simplified, minus, by distribution here, 4y plus 16. Because of that subtraction symbol, the numerator here can be rewritten as 8y minus 4y minus 16 all over the LCD. So when we go to reduce, we can combine like terms here. We end up with 4y minus 16 over the LCD. And I do have a solution here. It is not quite simplified just yet, amazingly. Mostly because our numerator still has some common factors. If I remove a 4, we end up with the following expression. And so a common binomial appears. And lastly, after we've sort of canceled out the common binomial here, we end up with a solution. In its simplest form, we end up with 4 over y plus 4.